These properties will now be determined for an unknown mineral. Most properties require the use of just two types of grains, the lowest interference colour grain and the maximum interference colour grain. Look at most grains to assess crystal form, cleavage and twinning. Other features such as inclusions and associated minerals may be important. Finally, use identification tables to identify the mineral. Grains of the unknown mineral are circled in red. Note the most obvious properties of these grains so that you can recognise other grains of the same mineral in the slide. Check the relief, colour, pleochroism, crystal form and interference colours. The unknown mineral has high relief and moderate birefringence and is pleochroic from yellow to green. Then scan the slide, looking for other properties such as cleavage, and find the lowest interference colour grain. For each field of view, open and close the diaphragm and rotate the stage in plane light and crossed polars. There's a possible lowest interference colour grain near the edge of this field. Shift the grain to the middle of the field. It remains almost at extinction. Check its pleochroism. It should be non-pleochroic if an optic axis is vertical. It's only slightly pleochroic, so we'll use it. And here are the properties we can determine from this grain. Select medium power, refocus, and change to the highest magnification. Refocus carefully and check the centering. If it's uncentered, the interference figure may not remain in view during rotation. Add the auxiliary condenser if fitted and open the diaphragm. Add the Bertrand lens and here's the resulting interference figure. Rotate to a 45-degree position, plate in. There's a fall in the northeast to southwest quadrant, therefore biaxial negative. Continuing the rotation, the isogyre stays relatively straight, so 2V is high. Check the sign again, plate in, and it's negative. The figure is in the right position to estimate 2V as it is rotated 45 degrees from when the isogyre was straight. The isogyre is nearly straight, so 2V is about 85 degrees. Rotate the stage so the optic plane is north-south, so Y is east-west. Without moving the stage, return to lower magnification. Check the colour in plane polarised light. Y is parallel to the polariser, so Y equals olive green. Rotating the stage shows why it is important to set Y east-west. Here there's a component of X in the Y colour, and there's the Y colour again. Now for the maximum interference colour grain. Here are the main properties it provides. Now find the maximum interference colour grain. Here's the maximum interference colour grain. X and Z will be in the plane of the stage. In plain light, the maximum interference colour grain changes from pale yellowish to dark green. So these are the X and Z colours. Set the dark green vibration direction east-west and fine-tune that position. Cross the polars. This is an extinction position. Rotate the dark green vibration direction northeast-southwest. Plate in, and the interference colours seem to rise to third order blue. Rotate 90 degrees to check, and the interference colours fall to almost black. Rotate back. That's definitely a rise, so the northeast-southwest vibration direction is Z. Rotate Z east-west again, and in plane polarised light, Z equals dark green. Then rotate 90 degrees to see the X colour. And there it is. So the complete pleochroic formula is X equals pale yellow, Y equals olive green, Z equals dark green. The absorption scheme is X less than Y less than Z. The maximum interference colour is second order blue, a retardation of about 650 nanometres. Find the intersection on the interference colour chart between the second order blue and the 30 micrometre thickness line. The resulting birefringence is about 0.022. Here's another maximum interference colour grain with better prismatic shape. The extinction is inclined, and the extinction angle seems to be about 15 to 20 degrees. We need to measure the extinction angle, Z angle C, and determine where the vibration directions are. First, rotate the C-axis exactly north-south. Note the stage reading. Rotate to the extinction position and note the stage reading again. Subtract the readings. 20 degrees is the result. The vibration directions at extinction are north, south and east, west as shown. The measured angle is between the C-axis and the north-south vibration direction. We know the vibration directions are X and Z, but we don't know which is which. Rotate the stage 45 degrees clockwise so the vibration direction that was north-south is northeast-southwest. Add the plate. There's a rise to third order blue. Rotate 90 degrees to check. There's a fall to black. So there's a rise in the first position. Therefore, Z is northeast-southwest. Rotating anti-clockwise back to extinction. Now think, where is Z? Z must be north-south and X is east-west. Now draw an orientation sketch showing the prismatic outline of the mineral, its cleavage traces and the C-axis, and add the vibration directions and extinction angle. And here are these features superimposed on the grain. Note how Z makes a smaller angle with C than X. X angle C is 70 degrees. Most grains show cleavage traces, as here. A few grains like this show two sets of cleavage traces at an angle which can be estimated or measured. In prismatic sections, we see only one set of these cleavage traces parallel to the prism. Returning to the grain with two sets of cleavage traces, note that each set is sharply defined. Thus, this grain is cut at right angles to the cleavages and the C-axis. To measure the angle between the two sets of cleavage traces, rotate the stage until one set is north-south and note the stage position in degrees. Then rotate the stage until the other set is north-south and note the stage reading again. The difference between the stage readings gives the acute angle between the cleavage traces, about 60 degrees. The extinction of this grain is symmetrical. That is, the vibration directions bisect the angles between the cleavage traces and between the crystal faces. Rotating in plane polarized light, note from the Pleochroism that the Y vibration direction, olive green, bisects the acute angle between the cleavages. Also, a vibration direction close to X, pale yellow, bisects the obtuse angle. This provides further information on the three-dimensional optic orientation. Some grains show straight internal grain contacts which are thinner than normal grain contacts. Note the different extinction positions for the two parts of this grain on either side of the contact. This represents the trace of a simple twin plane which bisects the acute angle between the cleavage traces. This prismatic grain appears untwinned. We should rotate the stage to check. The prism shows a twin plane parallel to its long axis. This twin plane is defined by the different extinction positions for the two parts of the twin. Again, this twinning is evident from Pleochroism in plane polarised light. If the mineral is monoclinic, this twin plane is probably parallel to 100. 010 can't be a twin plane as it is already a symmetry plane in monoclinic crystals. Here's a contact between the unknown green mineral and a grain of quartz. Use the Bekkie line test to compare the RIs of the two minerals. Close the diaphragm to observe the Bekkie lines and relief. Raise the focus, refocus. Raise the focus, refocus. The RI of the mineral is greater than 1.55, the RI of quartz. The high relief suggests delta N is about 0.15. We can rack down to see the opposite effect. Here the Bekkie line moves out of the grain, confirming the earlier result. Repeat this test at the edge of the slide at a mineral glue contact. The glue is isotropic under crossed polars. And the glue is dusty looking in plain light. Raise the focus, refocus, raise, refocus. Again, the Bekkie line moves into the mineral, so its RI is higher than for the glue. The mineral RI equals the glue RI plus delta N, equals 1.54 plus 0.15, which is about 1.7. The transverse prism sections with two directions of cleavage are characteristic of amphiboles. Inclined extinction suggests a clinoamphibole, and strong colour and pleochroism indicate green hornblende. Usually, mineral identification doesn't need all these properties to be determined. Plagioclase compositions can be estimated from extinction angle measurements. The extinction angles can be measured in grains cut normal to the A-axis, or the maximum angle method can be used. Here, each of the two sets of albite twin lamellae shows inclined extinction. The extinction angles can be measured relative to the 010 twin plane. The normal to A extinction method is described first. Find a grain cut normal to the A axis. The 010 twin planes must be vertical and therefore thin and sharp. The 001 cleavage traces must also be vertical and sharply defined. Note how the 001 cleavage traces change direction slightly where they cross the twin planes. And here I'm changing the focus slightly to emphasise the 001 cleavage, which isn't quite vertical. Now that we have the right grain, the extinction angle can be measured. Rotate the 010 twin planes parallel to the north-south crosswire. The twins should show the same interference colour in this position. Note the stage reading. Rotate one way until the first set of albite twin lamellae extinguish. Fine-tune that extinction position to get it precisely, and note the stage reading. The difference between the stage readings gives the extinction angle for this set of twins. Rotate the other way and repeat the procedure for the other set of twin lamellae and average the two extinction angles. For extinction angles less than about 18 degrees, we need to get the sine of the angle to get a unique composition. Find the acute angle between the 010 and 001 directions in the lamella at extinction. I'm uncrossing the polars so you can see the 001 cleavage traces better. Note that there is an acute angle and an obtuse angle. Here's the rule. If the acute angle, shown by the yellow arrow, is the more northward, the extinction angle is positive, as here. Here's another plagioclase for determination of the sine of the extinction angle. This is the extinction position for the broad lamellae and the thin set of lamellae extinguish around here. Find the 010 and 001 directions in this broad lamella at extinction. Note the resulting obtuse and acute angles. Here, the obtuse angle is the northernmost, which means a negative angle. Now look up the chart to determine the plagioclase composition. I'll now demonstrate the search for grains cut normal to A. This grain is unsuitable as the 010 twin plane is diffuse and the 001 cleavage is not visible. Here, the 010 twin plane is sharp, but the 001 cleavage is absent. The same applies here. 010 is normal to the plane of the section, but 001 is absent. Here, 001 is sharp, but 010 isn't. And this is the type of grain we want. Both directions are sharply defined. The maximum extinction angle method uses grains with sharp 010 twin lamellae. Grains like this are unsuitable. Here's the procedure for the maximum extinction angle method. Rotate the 010 twin plane exactly north-south and note the stage reading. Rotate until one set of twin lamellae extinguish and note the stage reading again. Subtract the readings to get the first extinction angle. Similarly, get the extinction angle for the other set of twins. Average the two extinction angles, provided they differ by less than about 4 degrees. Repeat this for about 10 grains and use the highest angle to read the composition off the appropriate graph. 2 possible compositions result for angles less than about 20 degrees. See your lab manual for further information. The chemical composition of plagioclase crystals commonly varies from the middle or core to the margin or rim. The core typically has a higher extinction angle than the rim. Thus, the core is more calcic than the rim, and this is called normal zoning. Plagioclase composition can also oscillate rapidly, resulting in sharply defined concentric zones which mark the former positions of crystal faces. Normal zoning is also present here. Notice how the extinction angle changes progressively from the core to the rim. Oscillatory and normal zoning are common in igneous rocks. A sharp break in composition can occur between the core and the rim, as here. The core has a positive extinction angle and the rim a negative extinction angle. Repeating that stage rotation, the more calcic plagioclase in the core has a higher positive extinction angle, the more sodic plagioclase in the rim has a lower negative angle. And here's a closer view of that sharp change near the rim. This crossover in extinction angles occurs for compositions around 20 mole% of anorthite, that is, oligoclase.